Hello guys, welcome to Makaut Smasher, where we simplify the complex subject for BTech CSE and IT students. Today, we will be exploring an essential foundation for engineering, Engineering Physics 1. This subject bridges the gap between the theoretical physics and the practical engineering. This is for the first semester. It equipping you with tools to understand the mechanics of motion, light behavior, electromagnetism, quantum principles, and statistical mechanics. We will cover the basics of the mechanics, optics, electromagnetism, quantum mechanics, and statistical mechanics, offering a glimpse into the fascinating principles shaping the modern technology. So, whether you are curious about how laser work, why materials behave differently under electromagnetic fields, or the quantum world's mysteries, this video is your starting point. So let's dive into the universe of engineering physics and lay a strong foundation for your academic journey. At first, mechanics. Mechanics deals with the motion of the objects under the forces and their interactions with the environment. It introduces the concept like the friction, constraint, and the role of the vector calculus in describing the physical phenomena. You will explore the idea of the potential energy surfaces where forces act as a gradient and differentiate between the conservative and the non-conservative forces. The conservation laws of energy and momentum provide the backbone of the mechanical system. Additionally, we will dive into the non-inertial frames and phenomena like the harmonic oscillation, damped oscillation, and resonance. The study also extends to the rigid body motion into 2 and 3 dimension, analyzing the moment of inertia and angular velocity vectors, essential for understanding the rotating systems. So now, optics, the second chapter. The optics is the study of the light's behavior, including its interaction with matter. This topic introduces the interference and the diffraction, explaining the distinction and the applications of the Fraunhofer and Fresnel's diffraction. Fraunhofer diffraction at single and the multiple light unveils the intriguing patterns of the maxima, minima, and intensities of the light. Diffraction gratings and their resolution power have significant application in the spectroscopy. Polarization phenomena such as scattering, circular and elliptical polarization, and optical activity are the key. Finally, lasers are introduced, it focusing on their principles, population inversion, and application in communication and medicine. Optics bridges the theoretical world of the physics and the practical realm of engineering. So now the electromagnetism and dielectric magnetic properties of the materials. This topic focuses on Maxwell's equation, the cornerstone of the electromagnetism, governing how electric and magnetic fields interact with each other. Dielectric materials, characterized by the polarization and the dielectric constant, are studied for their internal field effect, leading to the applications like capacitors. The Clausius equation provide the insights into the dielectric behavior. Magnetic materials are classified into types like the ferromagnetic, paramagnetic, and the concepts like the magnetization, permeability, and the hysteresis loops explain their properties. The study of the magnetic domains reveals the reasons behind the ferromagnetism. Electromagnetism's principles are vital for technologies like the transformer, motors, and the communication devices. So now, quantum mechanics. Quantum mechanics unveils the mysteries of the microscopic world, starting with phenomena like the black body radiation and the photon concept. The de Broglie hypothesis introduced the wave particle duality, verified through the experiments on matter waves. The Schrödinger wave equation provides a mathematical framework for describing the quantum systems, including the particles in a box and the quantum harmonic oscillator. The hydrogen atom's quantum mechanical model explains the atomic structure and the spectral lines. Quantum mechanics is a foundational for the modern technology, from the semiconductor to the quantum computing, making it a vital area of study in the engineering physics. So now the statistical mechanics. Statistical mechanics concepts or it connects the microscopic particle behavior to macroscopic thermodynamic properties. It introduced the microstate, macrostate, and the concept of the density of the state. Three major statistical distributions, Maxwell-Boltzmann, Fermi-Dirac, and Bose-Einstein, explain the behavior of the classical gases, electrons, photons, respectively. The study of these distributions enables the prediction about the thermal and the electrical properties of materials. Statistical mechanics is indisciplinable in fields like the materials science, where understanding particle interactions leads to innovation in the technology and the engineering domain. So, and that wraps up this brief overview of the engineering physics. We have touched upon the core topics that form the foundation of this exciting subject, from the mechanics to the statistical mechanics. These principles are not just theoretical, they power the technologies and the tools you encounter daily. Stay tuned as we dive deeper into each chapter and unraveling the mysteries of the physics, one concept at a time. Don't forget to like, share, and subscribe to the Makaut Smasher for more engaging content. Let's make learning physics as exciting journey together. Until the next time, keep smashing your goals.